So chapter 8 is dealing with confidence intervals. So we're going to use confidence intervals to try to estimate a parameter based on sample data. And chapter 8 is organized in a similar way to what chapter 7 was. Section 8.1 is dealing with confidence intervals in general, the basics, some terminology, just to get some basic understanding. Then in section 8.2, we'll deal with how to apply confidence intervals to proportions. And then in 8.3, we'll deal with confidence intervals and how they apply to sample means. All right, so in the last chapter, chapter 7, we looked at, okay, so here's a population, it's normal. And so what we talked about was taking samples from there, and possibly many, many samples, and creating a sampling distribution. Now, more often than not, we looked at approximate sampling distributions, but we knew what we learned what the theoretical sampling distribution should look like. And then we answered questions like, well, how likely are we to get a value of 15 or larger, for example, in an X bar? So we take one sample, we get an X bar value of 15, and we're like, okay, well, how likely was that to happen? And so we think about what's the probability that we would have something less than or equal to 15, or maybe greater than or equal to 15, something more extreme, whichever direction we wanted to go. This is completely, really unrealistic because we never really know what the population distribution looks like. We don't know what the population distribution looks like. We don't know what the population parameters are. And so really what we're stuck with is the following. Okay, so more realistically, that's it. We took one sample. From that sample, we might calculate an X bar, or maybe a p hat, depending on the situation. But here we're talking about means. So we found one X bar. Okay, so how do we use that? One statistic, one X bar, to try to estimate what the true parameter, in this case, since we're dealing with means, the mu is, and try to discern what the population distribution might look like. But more importantly, just kind of trying to estimate what the population mean is. All right, so let's pretend that I have what we're referred to as a mystery mean. So I have created some mean value, and I'm calling it M, and I stored that value, whatever it is, in my calculator. And then in your calculator under math, you have, and probabilities, you have an option that is random norm. So what that does is it randomly generates data from a normal distribution with a given mean, that's the unknown M, and 20 is the standard deviation from the population, and 16 is how many samples we would generate. And then what the mean function out in front does is it just calculates the mean of that and gives us the mean of the sample, or what would be the X bar. Now, assume that in my calculator, I have a value stored in M. So M is like a variable here. And you can do this in your graphing calculators. But in this case, you don't know what M is. And so we want to try to estimate that. And so what you could type this in your calculators, and let's assume that we did this and we got a value of 240.79 out of the calculator. All right, so again, what we've done is we've taken a sample of size, a simple random sample of size 16 from a normal distribution with unknown mean M and a standard deviation of 20. Now the calculator knows what the M is, it's just I'm not showing it to you. Okay, so and then we asked it to calculate the mean of that, and so the X bar, or the mean of that 16 data values that were taken from a normal distribution, is 20.79, 240.79. All right, so what we would like you to do is to think about, like, hey, what would be a good estimate for that mean, that mystery mean M? And so normally I would have you all, work in groups in class and talk about that. So you might just pause this video and think about, like, how could we use, how can we use that, the X bar to estimate? Maybe you would even do an interval, try to come up with a set of values that you think captures what the true mean is. All right, so hopefully you've sat and you've thought about it a little bit, so this is the data we have. So we know, we don't know what mean is, the mu, the unknown, mystery mean. We don't know what it is. The calculator has it in it, so there is a mean, but we just don't know what it is. We know the standard deviation of the population is 20, and the sample size is 16. So how can we try to estimate what that true mean is? All right, so first we have what's called a point estimate, and that would be the X bar. And this would probably be a fairly good, hopefully it would be a good estimate of the population mean. And quite frankly, it's the only data we have. So we don't have anything else to use. So that would be our best guess at this point. If we had to come up with an estimate for the mean, the 240.79, frankly, is all we got. All right, now it's not very likely that the true mean is exactly 240.79. First of all, I probably would have put in a whole number, an integer, probably not a decimal, but you don't know. So we know that it's not exactly 240.79. It's pretty safe to assume that it is not. So what we want to do is come up with some sort of interval of values that would capture that true mean. And so what should we use as the center of that interval? Well, it makes sense that we would use the 240.79 because frankly, that's all we have. So that's our best guess at this point. If we had to pick one value, it would be that. But we don't want one value because we're pretty sure that that one value is probably not the true mean. So we want to come up with some sort of interval. And so if we think about plotting that 240.79 on an interval, on a number line, we might want to say, okay, well, so how wide should that interval be? And so we could say, well, we could start with that value and go plus or minus 5. So we would get some sort of interval similar to this. Like, okay, let's count this as the interval and hope the mean is between those two. Well, why 5, right? Why use 5? We could also use 10, right? So the interval is a little wider. So we say 240.79 plus or minus 10, which would give us, of course, that interval from 230.79 to 250.79. And you're like, well, okay, maybe we want to go wider. And so what if we did plus or minus 15? So we have an interval now from 225.79 to 255.79. So how wide should we go? I mean, again, we would like to make sure that we're capturing the true mean. So we might want to go even wider. But the problem is that the wider we go, the less useful the estimate and resulting confidence interval is. And the next slide sort of demonstrates that. So here we have Garfield, and so he's watching the news, watching the weather forecast on the television, and the newscaster, the meteorologist says, taking a look at tomorrow's weather. The high temperature will be between 40 degrees, 40 below zero and 200 above. And of course, then Garfield says, this guy's never wrong. So of course, because that interval is so large that he's not going to be wrong. I mean, there's no way that the high tomorrow is going to not be between 40 below zero and 200 above. But how useful is that interval? If you asked your smart device, oh, what's the temperature outside? And it said, well, it's somewhere between 40 below zero and 200 above. It wouldn't be very useful. So there's a trade-off. The wider the confidence interval, the more likely it is that you've captured the true parameter that you're trying to estimate. But the wider it is, the less useful it is for as an estimate. All right, so if you're given one number to estimate, if you had to give, sorry, one number to estimate the unknown population parameter, then, and you're looking at population means, you're probably going to use X bar, like we saw in the mystery mean example. The X bar was the only estimate we have, so that point estimate is the one you're going to use. Now, if you're using population proportions, that you're trying to estimate population proportion, or P, then you will use the P hat. In both cases, these things are both called the point estimator. So it's simply the statistic that we got from our sample, all right? And so the actual statistic, the value of this statistic is called the point estimate. The statistic is sometimes referred to, though, as the point estimator. All right, so we learned in Chapter 7 that an ideal point estimator will have no bias, which means the sampling distribution of all the samples that you could possibly take would be centered at the true parameter value. So no bias, or an unbiased estimator. And also we would like low variability. One of the ways we can minimize the variability is to take larger sample sizes. All right, since variability is almost always present when calculating statistics from different samples, we must extend our thinking about estimating parameters to include acknowledgement that repeated samples could yield different results. Okay, so if we're going back to our mystery mean again, we had an X bar of 240.79. How likely is that to be? It's not very likely, but how close are we hoping our true mean is to this X bar 240.79? All right, so how would the sample mean X bar vary if we took many samples from our population, not all from the same size of size 16? So we can think of the population, we can think about taking lots and lots of samples, and as a result, we would have a sampling distribution. Again, this is all very theoretical because again, we only get one sample. Last chapter, we talked a lot about making many samples, or we did computer simulations. Here, we really are getting into the really nitty-gritty of it. We only have one sample. All right, so to estimate that mystery mean, we're going to use the X bar, like we saw on a couple slides ago, the 240.79, as a point estimate. So we have already established that, but how wide should our confidence interval be? Well, we know the sampling distribution will have a standard deviation of 5. That's the standard deviation of the population, 20, divided by the square root of 16, which is 4. So our sampling distribution will have a standard deviation of 5. We also know our sampling distribution is normal because we're assuming our population is normal. We use the random norm function on our calculator, so we know that population is normal. So even though our sample size is small, we know the sampling distribution is normal because the population distribution was normal. All right, so just right at this point, we're just going to use sort of a rule of thumb. We're going to use our empirical rule. Remember, 1, 2, or 3 standard deviations from the mean. So the 95%, that means 95% of all samples of size 16, right? That tells us the X bar will be within plus or minus 10 or 2 standard deviations from the mean. So if we look at here, we have the mean plus or minus 10, but the problem is we don't really know the mean, do we? We know X bar. So if X bar is within 10 points of mu, that also means that mu is within 10 points of X bar. So instead of looking at doing a confidence interval around the mu, because we don't know what that is, instead we put a confidence interval around our X bar. But it works just the same, saying how likely are we to have an X bar within 2 standard deviations of mu is the same thing as saying how likely are we to have mu within 2 standard deviations of x bar. All right, so the interval x bar minus 10 and x bar plus 10 will capture mu, the true population mean, about 95% of the samples. All right, so if we are estimating mu, right, we want to estimate mu, and we want to say that it's somewhere in the interval of 230.79 to 250.79. We'd be calculating an interval using a method that captures the true mu in about 95% of all possible samples. And so that's what it means. It doesn't mean that we have a 95% chance that we captured the true mean. That means if we repeat this process, take a sample of size 16, calculate its x bar, then go plus or minus 2 standard deviations of the sampling distribution. So plus or minus 10 from each of the x bars, then we would have lots of different confidence intervals, but 95% of the confidence intervals from those samples of size 16 would capture the true mean. And so sort of wrapping up here, the bigger picture. So we have an estimate, sometimes referred to as the point estimator. So the estimate either going to be x bar or p hat. In this case, we're dealing with this mystery mean, so we're dealing with means. So it's the point estimate plus or minus the margin of error. So 10 was the margin of error for us in that last example. The C% confidence interval just gives us an interval of plausible values for a particular parameter. Again, we're dealing with x bars, so for the parameter mu. So point estimate plus or minus the margin of error. So the difference between the point estimate and the true parameter should be less than the margin of error in C% of the sample. So that means in 95%, if we're using a 95% confidence level. So that just means that in 95% of the time, the interval will have captured that true parameter. All right, the confidence level C gives the overall success rate of the method for calculating the confidence interval. That is, in say 95% or C% of all possible samples, the method would yield an interval. So that would mean the x bar plus or minus the margin of error that captures the true parameter mu. All right, confidence level is the overall capture rate. So again, if we use this method to, take a sample of the same size, get that x bar from that sample, do plus or minus the margin of error, we would capture the true parameter, in this case mu, C% of the time. So if we look at this again, we have the population, we take lots of samples. Every time we take a sample, it would generate the x bar, and the resulting plus or minus 2 standard deviations would create a confidence interval that captures the true parameter C% of the time. So let's look at an app that will demonstrate this. Okay, so this app here that kind of comes with our book allows us to take samples from a normal population. So you can see the black normal curve represents the population distribution. The dashed red curve represents the sampling distribution, which makes sense because the sampling distribution has a standard deviation or a spread measured by the standard deviation, which is the population standard deviation divided by the square root of n. So we would, of course, expect the sampling distribution to be less wide. Okay, so I'm taking a sample of size 15. I have my confidence level with this app set at 95. And let's just take a sample and see what happens here. So I've taken a sample of 15 from the population distribution. The app took those 15, calculated the x bar, the yellow dots are the sample, individual sample values, The black dot, is the X bar, and then the line represents the confidence interval. So it's the X bar. In this case, since we're using 95% confidence, we know it's roughly 2 standard deviations, plus or minus 2 standard deviations from our X bar. So in this case, the X bar plus or minus 2 standard deviations created a confidence interval that actually captured the mean, which is represented by the green line. And so we could take another sample. And so in this case, we almost got the exact same X bar and confidence interval. Let's just keep taking a couple of samples. You can see every time the X bar is going to change, but since the confidence interval, the margin of error in this case, is based on the sampling distribution's width, we would expect those to all be consistent. You can see in this case, if you look down here, 100% of our samples so far have captured the true mean. And so we could just keep taking examples of these. And so we got our first red one. The red indicates that the X bar from that sample, plus or minus the confidence interval, plus or minus the margin of error that generates the confidence interval, failed to capture the true mean in that case. So if you look at our percent of hit, or the percent that capture the true mean, we're down to 96%, which is close to this 95. I mean, so that's what this confidence level of 95% means. It means if we take many samples from the population, and for each sample we calculate the X bar and then create a confidence interval using plus or minus the margin of error, and we use that procedure consistently and many times, the resulting confidence intervals will capture the true parameter in 95% of the cases. Now, we only did 27 total cases here, and all but one got captured, and so that's about a 96%. If we were to do this many times, you would see that the capture rate would hone in on that 95%, and that's what the confidence level means. All right, so we're going to be asked to interpret the confidence interval or to interpret the confidence level. So there are very distinct ways that they're expecting you to say this. These are good models, and I would use these as models for homework when you're looking at this kind of thing on the homework tonight. To interpret a confidence interval for an unknown parameter, say, this is how we want to say it. We are C%, so probably 95%, 90%, 99%, whatever the percentage is. So we are C% confident that the interval from, and then you give the actual values, from blank to blank, captures the actual value of, and then in context, say the parameter that you're trying to estimate. All right, we'll look at an example. And now that's very different than how we interpret the confidence level. The confidence level is really just the capture rate. It's talking about how often we would capture the true parameter if we use this procedure to take many samples. So to say that we are 95% confident is shorthand for, if we take many samples of the same size for this population, about 95% of them would result in an interval that captures the actual parameter value. So for 95% of those samples, the resulting X bar and confidence intervals, 95% of them would capture the true parameter value. All right, let's look at an example. Keep on walking. So a large company is concerned that many of its employees are in poor health, which can result in decreased productivity. To determine how many steps each employee takes per day, on average, the company provides pedometers to 50 randomly selected employees to use for one 24-hour period. After collecting the data, the company's statistician reports a 95% confidence interval of 47 steps to 73 steps. All right, so interpret the confidence interval. So say what you're supposed to say in words. So pause this and write that down. All right, so we are 95% confident that the interval from 4547 to 8473 captures the, and now you want to talk about the parameter in context, captures the true mean number of steps per day per employee for this company. All right, what is the point estimate? Now, normally you start with the point estimate, you come up with your margin of error, and you create your confidence interval. But here they give it to us in reverse. So calculate what your point estimate is. Again, pause this, calculate it, and then unpause it. So find the point estimate for the interval as well as the margin of error. All right, so the point estimate is just the midpoint between those two values. So we would add them up, divide by 2. That would be the midpoint. So 6510 is the X bar that the statistician calculated. And then the margin of error is simply the distance from that X bar out to the endpoints of your interval. So if you want to just take the upper value of 8473 and subtract the X bar, you get 1963. So that is the margin of error. All right, so recent guidelines suggest that people aim for 10,000 steps per day. Is there convincing evidence that the employees of this company are not meeting this guideline? So are they meeting this guideline or not? What do you think? We will have better ways of answering these kinds of questions in later chapters, but for this point, at this point, we look at the confidence interval, right? So the confidence interval is a range of plausible values for the parameter that we're looking for. So our confidence interval, 8447 to 4547 to 8473, does not capture 10,000. So in other words, 10,000 is not in there. And so 10,000 does not seem to be a plausible value for the mean because it is outside in quite a substantial way. I would add outside that value, outside the interval. So because all the values in the interval are less than 10,000, there is convincing evidence that the employees are not reaching their 10,000 goal because that value of 10,000 is not contained within the confidence interval, which again gives us a range of plausible values for the parameter we're trying to estimate. Okay, so if you're looking for an example of this because this example used sample means, sample proportions, go look at page 481, and that will give you an example of creating confidence intervals for sample proportions. All right, so we have 5 homework problems. These are due next class.